Hello friends, welcome back to our course on spectroscopic methods of analysis. In today's session, we will continue our discussion on the basic aspects of spectroscopy and take up two things primarily. One, the quantum mechanical nature of atoms and molecules, and secondly, different modes of interactions which are possible between the radiation and matter. The session is planned as follows, that is, to begin with, we will briefly recall what we did in the previous session. Thereafter, we will take up the quantum mechanical nature of matter, that is atoms and molecules. Having done that, we will move on to different modes of interaction possible between radiation and matter. And then we will take up what are different prerequisites, that means what are the preconditions required for the interaction of radiation and matter. And then towards the end, we will sum up what we do in today's session. Let us make a beginning by recalling what we did in the previous session. In the previous session, we basically started by defining spectroscopy to be the interaction of radiation and matter. Having defined that, we primarily focused on to the nature of electromagnetic radiation. We started by describing the wave aspect or the wave model of electromagnetic radiation and discussed in detail about the characteristics of EM radiation there. Thereafter, we took up the quantum mechanical or the particle model of EM radiation, and then we briefly discussed about electromagnetic spectrum, that is a spread of different kind of EM radiations what we can have. Okay, so with this brief recall, let us move on to today's session and start by talking about what is the quantum mechanical nature of atoms and molecules. Now, you would recall from your earlier studies that according to the Bohr's model, basically an atom can be seen as we have a tiny nucleus there, and then there are electrons which are into different orbits over there, and these are stationary states or the quantum states there. To put it straightforward, essentially what we can say is that is the electronic energies of the electron in an atom are quantized. That means atoms have got quantized electron energy levels there. And if we go to atom like say sodium, now we know that the energy level diagram is little complicated here because of the interaction of orbital motion and the spin motion spin of the electron over there. But primarily what we can have is that is for atoms the electronic energy levels are quantized, that is regarding the nature of atom there. But if we move on to the molecules, we find that molecules are much more complicated because we know that molecules are obtained by combination of atoms. So, we have got atom 1, atom 2, the two come together, the electrons will overlap, and that variety of models we know of the combination of atoms to give molecules there. In molecules also we got at least two nuclei are there, and then there are electrons which are into different orbital different energy levels over there, which according to molecular orbital theory we know what they are. Now, when you move on to the molecules, it is not only the electronic energy levels which are quantized, because the molecule can execute different kind of motions, like molecule can rotate, there is a rotational motion there, or the two atoms in a molecule can vibrate, there is a vibrational motion there. So, in case of molecules, what you find is that there are different energies which are quantized there. Let us look at that. Now, this actually shows you the different electronic energy level. It is a schematic diagram over there. So, this is electron energy level number 1, 2, 3 and so on and so forth. Now, if you look at one electronic energy level, we find that within a given electronic energy level, there are different vibration energy levels possible over there. That is, if the molecule happens to be in say E1, the first electronic energy level, within that E1 it can be in any of the vibration energy levels over there. And if you go further between these two vibration energy levels also, we find that within the vibration energy levels there are different rotational energy levels possible there. That means, in case of a molecule, the electronic energies are quantized, the rotational energies are quantized, as well as the vibration energies are quantized there. Now, this whole thing translates into the following diagram over here. Let us look at this. Essentially what we have is, this is my E0, the electronic ground state there, then this is my E1, that is the excited state over there. within one electronic energy levels, there are different vibration energy levels which are denoted as V 1, 2, 3 and so on and so forth. And then within a vibration energy level, there are rotation energy. It is purely a schematic diagram. What we can observe from here is that is the rotation energy levels are quite close by, whereas vibration energy level, the energy delta E value is larger than that, and for electronic energy levels this difference is much larger. That means we have got the following order there. Delta E rotation is very tiny, maybe a few centimeter inverse, whereas in case of delta E vibration it is about 1000 times more, it is about a few thousand centimeter inverse, and electronic energy levels are about another 1000 times higher than that. And that means these energies are quantized, and that is the kind of disposition we have in case of molecules there. Okay. Now, let us move further and see that before we continue further, let us briefly recall our EM spectrum what we discussed in the previous session. We recall that electromagnetic spectrum basically refers to the spread of different kind of electromagnetic radiation which are there. And what we have to see here is that is the EM radiation of different regions have got different energies, because this is long radio waves there, the energy is very small, and then we come down to microwave, energy is slightly larger, IR is still more visible, and UV they have got still higher energy, and so on and so forth. Energy is increasing in this particular direction there. Now, what does it mean? What does it mean is that is if I take up an EM radiation from a given region of the spectrum, it will have certain range of energies there, and these energies actually when the radiation comes and interacts with matter, what happens? This EM radiation which is coming has certain amount of energy. This is matter where quantized energy levels are there. So, this radiation comes and interacts with this and causes change in the energy levels of the molecule over there or the matter over there. Now, this is basically our domain of spectroscopy. Now, what we see from here is, say if I have, say I am taking radiation from microwave region, the energy is such that it is a small amount of energy, it can only make excitation into the rotation energy levels. It cannot really disturb the vibration or electronic energy level of the molecules there. Whereas, if I come to say radiation in IR region, this has energy sufficient enough to cause vibrational transitions. Similarly, visible and UV they can excite electronically the molecules over there. So, essentially what happens is radiations of different regions of EM spectrum can cause variety of transitions in the molecules there, and that is what basically is the our main focus on spectroscopy there. Okay. Now, let us move further now and see that what are different possible modes of interaction of radiation and matter, because spectroscopy we define as the study of interaction of radiation and matter. Now, in what are the possible ways in which the radiation and matter can interact? Let us learn about that. And when the two come together, that means when the radiation comes and interacts with the matter, there are three possibilities. One is that the radiation is absorbed, this is called as absorption of radiation, or it may so happen that the matter is at excited state already in having high energy, it can emit radiation there, that is the second possibility. The third possibility is that there can be the scattering of radiation there. Let us learn about each one of them one by one. Let us begin with what is the meaning of absorption of radiation. Absorption of radiation basically refers to, that means you have a molecule or any system of matter, it could be atom or molecule, anything put together. So, we have a matter there, atom or molecules. We have radiation there, radiation comes and interacts with this. In the process what happens is, say this is my molecular energy levels there, E1 lower energy, E2 is of higher energy there. The system is to begin with is in a lower energy level E1. Now, radiation comes, let the radiation come as a photon there. So, what we see is as per the quantum mechanical description of radiation, we know that it is stream of particles there, stream of photons there. Now, suppose a photon comes and strikes the molecule in a lower energy state there, the molecule can pick up energy and go to higher energy state. This process is called as excitation, and that means the molecule now becomes excited, and this refers to the absorption of radiation there. Now, if we go further and see that in case of atoms, what do we have? In case of atoms, we mentioned earlier that is only the electronic energies are quantized there, and if I give a radiation there, so what will happen? There will be an electronic excitation, the system will go from a lower energy level to a higher energy level. This basically I am showing here in terms of the energy level diagram of sodium atom there. And this kind of an interaction, that means absorption of radiation by a molecule or an atom and consequent kind of excitation, that actually forms the basis for atomic absorption spectroscopy. We will talk about in detail about this at a later stage. Okay. Now, when we move on to the molecules, what we find is there are a variety of possibilities now. What are the possibilities? One possibility is that we give radiations there, and it is just that only the rotational excitations take place. That means the system goes from a given rotational energy level to higher energy level there, and this actually forms the basis for microwave spectroscopy. Rotational excitation primarily means that molecule is rotating at certain frequency, a given energy, it starts rotating faster. So, that is the meaning of excitation there. If we go further, and another possibility is if I give radiation of appropriate energy, what can happen? There can be transitions from say a given vibration energy level to higher vibration energy levels there. This forms actually the basis for our IR spectroscopy. This again we will discuss in much detail later on. Okay, this is one method by itself, we will discuss in great length over there. Another possibility is that in case of molecules, now suppose I give energy in the say UV or visible region, what can happen is you can have this kind of a possibilities. What do we see here? That is, to begin with, our system is at say E0, E0 is the ground electronic state, and within E0 it is in the V prime level or V0 level over there. When I have given energy, the system has gone from here to E1 level, that means there is an electronic excitation. Simultaneously, you can see that it is from V0, it has come to a V1 level there. So, there is a vibration excitation as well. Thirdly, what we see is that within this vibration energy level, the system has gone to say J is equal to 3 or J is equal to 4 level there. So, we find that if you give energy sufficient enough so that there can be electronic excitation in the molecule, that actually is accompanied by vibrational as well as rotational transitions also. Okay, that is very important, because that leads to, we will talk about that in the next session when we talk about the nature of spectrum there. Okay, let us move further. Let us move further and see that this, as I mentioned earlier, forms the basis for our UV visible spectroscopy or electronic spectroscopy. Okay. Now, what basically happens experimentally? What do we have is, here I am showing a small container there called as a cuvette there, and this just depicts that there is a molecular system over there. And what happens is, when some radiation comes, and what you find is the radiation is coming with a kind of intensity or the radiated power as P0. Now, when this gets in there, part of it gets absorbed there, and what comes out is a transmitted radiation of lesser intensity there. So, this actually forms the basis of our application of this. We will talk about that maybe in the next session and thereafter. Let us move further. We mentioned that the energies are quantized there, but in certain cases we find that this quantization does not happen on its own. It is some kind of a medium is required for that, and that happens is that typically we need a magnetic field over there. So, this could be electron spins there or nuclear spins of certain kinds. Now, if you have got this kind of system, they initially are randomized. That means the nuclear spins are oriented in all possible directions there, or even saying as of electronic spins also, they are randomly oriented there. But if I apply a magnetic field, then what happens is this nuclear or the electronic spins, they can either align with the field or against the field, because that is the effect of the field there. And this alignment actually leads to quantization there. That means a system which is aligned with the field has got lower energy, and if the spin is aligned against the field, it is of high energy. That means in the absence of the field, there was no quantization there. The moment I apply field, this comes into play, and we got two energy levels there. And there can be a possibility of giving a suitable radiation, and there is a transition from level E1 to E2. And this actually forms a very important domain of NMR and ESR spectroscopies there. But mind you, the requirement here is that we must have a external field over there. In the absence of field, this phenomenon does not come into play. We will talk in details at a later stage. And in terms of experimentation, basically what we do is, we take the sample here, put into a magnetic field there, and then you give some kind of energy input in terms of a radio frequency which is getting in there, and RF output is taken there, and that is how this is actually experimentally performed over there. Okay. Let us move further. Let us move further and then see that we have just talked about the interaction of radiation and matter, but there are other ways by which matter, atoms or molecules can get excited, and some of these happen to be, say, we can do bombardment with electrons or some other elementary particles. That's again essentially what is excitation. Excitation basically is system is at lower energy level, you provide energy in some form and the system will get higher energy level. That is the meaning of excitation. We did it in terms of the radiation to as we just discussed there, or other possibility could be we give high potential over there, high potential alternating current, that also can lead to excitation there, or maybe we can have a spark, arc or flame, that various means of exciting a molecular system over there. Now, this also we will be taking up when we talk about atomic spectroscopy and things like that. Now, what next? What next is that I have a system to begin with at lower energy level. I have given some energy in form of radiation or other means as I mentioned here. The system gets excited there. What happens thereafter? What happens thereafter is that this excited state can relax down. Let us look at this. There is a molecule here. At low energy level there, I give some energy in the form of radiation or other means there. This molecule gets excited, has high energy now. Then this molecule is not in isolation, it is moving around and there are other systems around this. So, what can happen is this molecule at excited state can interact with other molecules of the neighborhood, give energy to them and come down to lower level there. This is called as a relaxation which is non-radiative, because there is no radiation involved in this, and that is how do we show that M star here it basically indicates an excited molecule there which comes down to a lower level by giving energy to the neighboring molecules there, and some that energy actually is expressed in terms of heat, that means the temperature of the system slightly increases there. This is one non-radiative mechanism of relaxation there. What are the other possibilities? That is the next one which is very, very important for us, and that is basically called as emission there. Emission basically is, that is, we have system at high energy level there, the system is coming to a lower energy level, and this relaxation is accompanied by some kind of emission of radiation there. That is why it is called as a radiative relaxation there. Let us look at this. That is what happens there. That is, system initially was at high energy levels there, it comes down to lower energy level, and then this difference of energy comes out as a photon there. That is called as emission there. Okay. Now, for emission to take place, excitation which preceded that could have been any possible ways. It could be thermal, radiation or chemical means over there. So, essentially radiative relaxation basically means emission of radiation which is accompanied by the relaxation of the molecule there. Okay. Let us go further. Let us go further and take up an example for this. You must have done some kind of a salt analysis wherein you do a flame test. Typically, the flame test for sodium shows up a yellow flame there, and this yellow flame basically is because of emission of radiation in the visible range, and that actually can be shown as follows. That is, to begin with, the system is at higher energy level, and then because that higher energy level is achieved by putting that sodium into the flame there, because I am giving thermal energy by which the sodium ions have got excited there. Now, when they relax down, they give out the following two radiations there, and that is what is seen as the yellow color there. So, this basically is a kind of an atomic emission spectroscopy in a way. Okay. Let us go further. Let us see what happens in case of molecular system. In case of molecules, what do we have? We got electron energy levels, and there is a quantized vibrational and rotational energy levels there. Now, suppose I take a molecular system and make it excited in any possible ways, be it thermal or other means there. Once the system is at higher energy level, what happens is this actually can relax in the following way. That is, to begin with, molecules at higher energy level there, it collides with neighboring molecules, gives out part of its energy and comes down to a lower excited state over there, and then thereafter it comes down with the emission of a photon there. That means, in this case there is a non-radiative deactivation, say from here till here, and then thereafter there is a radiative emission there. This actually is the basis for our fluorescence and phosphorescence spectroscopies, which again will be taken up later. Okay. Let us continue and see that there are two more phenomena. I am sure that you are familiar with what is called as chemiluminescence and bioluminescence. Chemiluminescence basically is that certain chemical systems, there are certain chemical reactions which are accompanied by emission of radiation there. And this firefly, I am sure that you are familiar with. In the case of firefly, this radiation which comes out there, that actually is based on the biological, there is a biological reaction taking place there, and that actually forms the, that means because of the biochemical reaction, there is a emission of radiation there. So, chemiluminescence and bioluminescence also involve emission of radiation there. Okay. Let us go further. Please look at it little carefully, closely. Energy is coming, the system has got excited now, it relaxes and comes down to ground state over there. So, that is what basically is emission of radiation there. Okay. Let us look at yet another way of interaction of radiation and matter, and that happens to be the scattering. Essentially what happens is the radiation comes, interacts with matter, and part of it gets scattered there. Let us look at it. You have a sample here, radiation comes there, strikes it over there, part of it gets reflected back because of the container there, and then some radiation comes out as a transmitted radiation. But in addition to these two, what we find is in all around there, in all possible directions, there are certain radiation which comes out as a scattered light there, and this scattered light typically is measured in a direction perpendicular to the direction of incident radiation there. And this is actually a very important phenomenon, because what happens is this scattered radiation actually consists of variety of frequencies there. That means I have a system there, I give radiation of certain frequency that interacts and gets scattered. In the scattered radiation, we find there are two components there. The major component happens to be the radiation which is of the same frequency as that of the incident frequency there, and that actually is called as a Rayleigh scattering. In addition to that, a small component, very tiny component, has frequencies which is either slightly more or slightly less than that of the incident radiation, and that actually is called as Raman scattering, and that forms the basis for what is called as a Raman spectroscopy. Very, very important phenomenon. Okay. Let us continue. Let us continue and understand that there are other possible means of interaction between radiation and matter. We talked about only three possibilities: absorption of radiation, emission of radiation, and scattering. There are other possibilities, could be reflection, refraction, interference, diffraction, and many more things over there. These actually are the bulk properties of the system there, and that is what we are not interested in. What we are interested in is that how does a matter per se, a molecule or an atom, interacts with radiation, and what happens as a consequence of that. We are not interested in the bulk properties of the system. Let us go further and see that what are the prerequisites. Let us understand. I said that we have matter, we have got radiation. Radiation comes, interacts with matter, and something happens there. That is what we study there. But we raise a question, is it that any kind of radiation will interact with any kind of matter and things will happen? The answer to that is no. The answer is that it is not that any radiation will interact with any molecule or any system for that matter. There are certain kind of prerequisites there. That means we have to have some kind of a mechanism for the interaction of radiation and matter to take place. In absence of that, the two will not interact and we will not be able to get the so called information from there. And those preconditions, or they are called as the prerequisites, and that is very, very important there. That means for the molecule and the radiation to interact, certain conditions have to be met, and they are called as prerequisites or the necessary condition for the interaction to take place. Let us take an example there. Now, let us look at, say I am talking about the rotational motion. Let us take the example of some molecule of HCl. I am showing a small molecule over there. This is hydrogen atom there, this is chlorine atom there. The two are bonded together. Now, as shown over there, it has certain dipole moment which is shown as a small dot over there. Now, let us imagine now that this molecule of HCl starts rotating. This is vertical right now, it starts rotating like this. When it rotates, what happens to dipole moment of this? Let us look at this animation here. So, what do we see? What do we see is that as this molecule of HCl is rotating, we find that the dipole moment keeps on changing there, because when it was in this orientation, dipole moment was somewhere here. The moment it rotates a little here, about say 30 degrees or so, this is dipole moment. It comes like this. So, at this orientation, it is somewhere here, and so on and so forth. So, what we find is that as this molecule of HCl rotates, it generates a oscillatory dipole moment there, and that is very, very important. What happens is this is my EM radiation we are familiar with. I am just showing the electrical component of EM radiation that is there, and this is the oscillatory dipole which I have been able to generate because of the rotation of HCl molecule. Now, the two will interact now. Once the frequency of radiation and that of the oscillatory dipole moment, the two match, then there is an absorption of radiation there. That means the oscillatory dipole moment provides a mechanism for the interaction of radiation and the matter there. So, energy is absorbed there. Now, let us take second example there. Now, suppose instead of HCl, I take hydrogen molecule. The two atoms are identical, it is a homonuclear diatomic molecule. When that rotates, to begin with, there is no dipole moment. As it rotates, there is no dipole moment at all. None of these orientations have got any dipole moment there. So, this molecule of H2, that is hydrogen molecule, does not interact. I mean, the rotational motion of this does not interact with the microwave radiation. So, we say that HCl absorbs microwave radiation, whereas H2 does not. Or in other words, we can say HCl is microwave active, hydrogen is not. So, we find that the prerequisite here is that the rotational motion of the molecule must be accompanied by some kind of a oscillatory dipole moment change. That is a prerequisite for the rotational spectrum to be observed there. Let us take one more example there. Now, if I look at say vibrational motion, the prerequisite here is that the molecular vibration must be associated with an oscillatory dipole there, similar condition there. Let us take a look at this picture here. Now, what you see is that this shows the two modes of vibration of CH2 in a organic molecule there, that is CH2 group over there. What you find is, as in case of the rotation of HCl molecule, these also are accompanied by generation of a oscillatory dipole moment there. So, this again we find that this is my EM radiation, this is oscillatory dipole, the two will interact and there is a energy absorption will be there. And we say that these two modes are IR active, because if they are not accompanied by an oscillatory dipole moment generation, the two will not interact, that they will be called as IR inactive mode. We will talk in detail about all this later on. Now, similarly what we have is, for all possible spectroscopies, there has to be a mechanism, that is a prerequisite. When we talk about those spectroscopies, we will talk about the prerequisites over there, but for right now basically I wanted to demonstrate that there is a pre-requirement for the interaction of radiation and matter to take place there. For the spectroscopy also there are certain prerequisites required there. Okay. Now, let us sum up what we have done today. What we have done today is basically we started by reviewing the contents of the previous session. Thereafter, we discussed about the quantum mechanical nature of matter, that is atoms and molecules. We realized that in case of atoms, the electronic energies are quantized, whereas in case of molecules, the electronic, vibrational and rotational, all kind of energies are quantized there. Thereafter, we took up different modes of interaction of radiation and matter. We discussed primarily the absorption of radiation, emission of radiation and scattering of radiation. So, there are three important modes of interaction of radiation and matter. And thereafter, we discussed the prerequisites for the interaction of radiation and matter. In the next session, what we will do now is, we have seen so far that we defined spectroscopy to be interaction of radiation and matter. In the previous session, we talked about what is the nature of EM radiation. Today, we talked about the nature of matter and the modes of interaction between radiation and matter. In the next session, we will talk about what is the consequence of this interaction, that is, what is a spectrum, how does it look like and what are the characteristics of a spectrum. That will be taken up in the next session there. Thank you.